Topic 8, Acid and Bases. 8.1 Theories of the Acid and Bases. This is the first section of Topic 8, Acid and Bases. Arrhenius theory of acid and bases. There are two known theories of the acid and bases, and first one is called Arrhenius theory of acid and bases. Okay, this theory is first proposed. There are two known theories of the acid and bases. There are two most known theories and acid and bases, and then one is proposed by the Swedish chemist named August Arrhenius. So we call this theory Arrhenius theory. Okay, and according to him, acids are substances that dissociate in water to produce hydrogen ions, and bases are substances that dissociate in water to produce hydroxide ions. However, his theory had limitations, okay? Because some of the compounds act like acid and bases that don't fit into the standard definition. Oh my god, right? So we don't really use this theory in IB chemistry. We use Bronsted-Lowry theory of acid and bases, okay? This theory is proposed independently by the Danish chemist and English chemist, okay? In same time, they proposed exactly same theory. Okay, so that's the reason why we named this theory as Bronsted and Lowry. We got the names from these chemists. Okay, and this simply considered as the theory of the proton transfer. Means this theory simply states that like acid is a proton donor and base is the proton acceptor. That's how they propose it. Okay, means acid in the reactant side, okay, this acid is capable of having a proton removed. Okay, so it is capable of donating a proton. Same thing with the base, but base in this case is capable of removing or taking a proton, means they are capable of accepting a proton. Okay, so what this means, acid will give off, okay, will give off its proton to base. Okay, so when that happens, when acid give off a proton, it becomes a base. Okay, and when base accepts a proton from acid, it becomes acid. Okay, so this side here happens in the reactant side. Okay, this side here happens in our product side. Okay, so we named this process or this product as the conjugate base and conjugate acid. So it means when acid react to form bases, or when base react to form acid, okay, we call this acid and base pairs conjugate acid and base pairs. Okay, and they're only different by just one proton. Means this acid here and this conjugate base are called conjugate pairs, and they only differ by just one proton. Okay, so your question must be now at this point is how to tell if something is an acid or base, right? We can tell something is acid and base by using the bouncing hydrogen rule. Okay, how to use the bouncing hydrogen rule? The first step you need to do is you first need to identify how the hydrogen moves from left to the right in the chemical reaction means how hydrogen moves from the reactant to product in the chemical reaction. Okay, so this, if you look at this one, hydrochloric acid, okay, I mean it's very obvious, right? HCl. You can see that there's a one less proton with this ion, right? So we can say this is giving off a hydrogen, okay? And this one has a less proton than this one less proton than this reactant, right? So we can say this is the acid and this is its conjugate base. So it's like conjugate pair. Okay. This is how you use the bouncing hydrogen loop. Okay, so let's go over this example together. We have to list the conjugate acid-base pairs in the following reaction. So we're going to identify which one has one less proton in the product. Okay, so first one is CH3COOH. This is our acetic acid. Okay, and it seems like this proton has been given off. That's the reason why we have this ion, right? We have, compared to this reactant, we have a one less proton on the product side. Okay, so we can say this is the conjugate base of this acid. Okay, then same thing, we have water, H2O here, and the hydronium ion on the product side has one more proton than the H2O. So we can say this is base and this is the conjugate acid. Okay. Then let's do these questions together. So now question number 1, we have to write the conjugate base for each of the following. So that means all these are acid. Okay, and we have to write the conjugate base. Remember, conjugate base has the one less proton, right? So H3O plus one less proton means H2O, and H3 one less proton means we are taking this proton away, right? So it means we have NH2 minus, because we're going to have a lone pair, lone electron, right? Same thing with the H2CO. We're going to take away one of the electron. That means we're going to have a one lone electron left over. So we're going to have HCO3 minus. Question number 2, we have to write the conjugate acid for each of the following. That means these are our base. Consider as base. Conjugate acid means it has one more proton, only one more proton, right? So NO2 will gain a proton. Okay, it will become HNO2, right? Because it is going to stay stuck to this electron left over, right? Same thing with the OH minus, is going to combine with the hydrogen ion or proton, so it will become water, H2O. CCO3 2 minus, we're going to have a one proton. We're going to have a one proton attaching to this one of the electron, right? Lone electron. So it will become HCO3 minus. Okay, so now we need to know what is meant by amphiprotic species. Okay, so before we saw that, like from the previous example, amphiprotic species. So we now need to know what is meant by amphiprotic species, right? So before, like in the previous example, we saw a case where water reacted as a base, okay, and where water acted as base and where water acted as acid, okay? So substances which can act as Bronsted lowering acid and bases, meaning that they can either accept or donate a proton, just like water, H2O, that we saw with the previous example, is called amphiprotic species. Okay, the following features enable them to have this double identity. Okay, they're like a double spice. They can act both acid and as base. To act as a Bronsted lowering acid, they must be able to dissociate and release hydrogen ion, and to act as a Bronsted lowering base, they must be able to accept hydrogen ion, which means they must have a lone pair of the electrons. So, for example, like something like water, it can lose a proton, become OH minus, right? Or it can gain a proton and become hydronium ion. Okay, that's the reason why it's called amphiprotic species. So water is a prime example. It can donate hydrogen ion and it has two lone pairs of the electrons. Okay. Also, so means like we already went over these examples, but I'm going to go over them again. Water can ionize itself, right? So water and water react together and produce hydronium ion. Okay, and water can react as a base with the CH3COOH, the weak acid. Okay, and water can react as an acid with NH3. Okay. Okay, so we have to write the equation to show HCO3 minus reacting with the water, and when HCO3 minus acting as acid and HCO3 minus acting as a base. Okay, so question A, the HCO3 minus is acting as acid. Okay, then water will be your base, right? Okay, so water going to be liquid and HCO3 minus is ion, so it's going to be aqueous. Okay, and when it react together, okay, since the HCO3 minus is your acid, it's going to give off its hydrogen ion and H2O will accept it, so we will produce CO3 2 minus aqueous plus H3O plus aqueous. Okay. Same thing with the B, but in this case, the HCO3 minus is acting as a base and water is your acid. Okay, that means water will give off one of its hydrogen to HCO3 minus. That means HCO3 minus will gain a hydrogen and it will become H2CO3 aqueous plus OH minus aqueous.